Okay, let's kick things off. Welcome, everyone, to this deep dive.
Hello. Yeah, we've got quite a bit of material here, notes, some examples, different ways of explaining things.
All focused on, well, percent and percentage, something you really see everywhere.
Absolutely. And our job today, sort of wading through all this, is to pull out the real core ideas.
Make it clear, make it useful, give you that shortcut to getting it.
Exactly.
So let's start with the real basics from this material. What even is percent?
The notes define it pretty simply. Percent just means for every 100. That's the heart of it.
Right, percent for every 100. You see PCs sometimes, apparently, but mostly the percent sign.
And percentage, often used the same way, right?
Yeah, mostly. Though technically, the notes point out a percentage is a fraction where the bottom number, the denominator, is specifically 100.
Ah, okay. So the top number, the numerator, is the rate percent. Like 8 over 100 is 8%.
Exactly. But, in practice, like you said, people use percent and percentage almost interchangeably.
It's all about thinking in terms of out of 100, a standard way to compare parts.
Okay, so if that's what it is, how do we work with it? Converting seems key.
Definitely. The material gives clear steps to turn a number into a percent.
You multiply by 100, stick the percent sign on the end.
Yeah. Like the example, 35 times 100 is 60, so 60%.
Or a decimal, 0.45, times 100 is 45. Slap on the sign, 45%.
You're basically just scaling it up.
Yeah.
What would this be if the total was 100?
Makes sense. And going the other way, from percent back to a fraction or decimal.
Just reverse it, divide by 100, and take off the percent sign.
So 45% divided by 100, that's 0.45.
Right. Or as a fraction, 45 over 100, which simplifies down, let's see.
To 920, according to the notes here. It's really just shifting that decimal point, isn't it?
2 places, exactly.
And the material gives us some core formulas for actually using this stuff.
Yeah, like finding x as a percent of y. That's a common one.
How does that work again?
Simple formula. You do x divided by y, then multiply the result by 100%.
Okay, so the example was 5 is a percent of 20.
Right, so 5 divided by 20, that's 0.25.
Then times 100% gives you 25%.
Yeah, finding that proportion. What part of 20 is 5? Expressed out of 100.
And the other big one is percentage increase or decrease. Super practical.
The formula there is the change, how much it went up or down.
Divided by the original amount. That seems important.
Crucial. Always divide by where you started, then times 100%.
And these examples in the source material really show how this plays out.
They do. Take the salary one. The guy spends 65% of his salary, saves 525.
So if he spends 65%, the immediate question is what percentage is left? What's he saving?
He's saving the rest, right?
Yeah.
100% minus 65%, that's 35%.
Okay, and that's the key connection the notes make. That 35% is the 525.
Exactly. Once you know that 35% of the total salary equals 525 rupees, you can work backwards.
To find the full salary, which the notes calculate out to 1,500.
It shows how knowing a part and its percentage lets you find the whole thing. Pretty neat.
And the percentage error example? Also quite good.
Yeah, like reading 4.0 incorrectly is 4.48. The error itself is 0.48.
But just saying 0.48 doesn't tell you much on its own. Is that a big error or a small one?
Right. Depends on the original number. That's where percentage error comes in.
You calculate the error amount, the 0.48, as a percentage of the correct original number.
So 0.48 divided by 4.0, then times 100%.
And the example shows that's 12%, which tells you something more meaningful.
It gives you the relative size. A 12% error is pretty significant in many cases. That 0.48 matters more relative to 4.0 than it would to, say, 400.
So yeah, going through this material, it really lays out the fundamentals quite well.
From what is percent, out of 100.
To converting smoothly between formats, percents, decimals, fractions.
And then using it in real calculations, like that salary or the error example.
Understanding these basic mechanics really is crucial for making sense of, well, tons of information out there.
For sure. It's just part of understanding data.
So thinking about this, especially the increase-decrease stuff, it makes you wonder, based on these kinds of problems, if you increase something by a certain percent, say 10%, and then you decrease that new amount by the same percent, 10%, does the order you do it in make a difference?
Know what you say.
And maybe more importantly, does doing a 10% increase and then a 10% decrease actually get you back to where you started?
That's a fantastic question to chew on. Applying these ideas, sometimes the results aren't quite what your intuition might tell you. Something for you to think about.